So let's continue our look into the null space. Now yesterday we had a few examples, but in some sense they were very special examples, and I don't want you to think that that extrapolates to all examples. So let's have here 3 equations and 4 unknowns. We don't have enough equations, and our matrix of coefficients would be 1, 1, 3, 1, 1, 3, 2, 4, 10, 3, 5, and 13. You can take the matrix of coefficients, which would make our matrix A. You could make the augmented matrix if it's all zeros as well. You're going to end up with the same thing. This is the row-reduced form of the matrix of coefficients. And if we had done the augmented matrix, there'd be another 0, 0, 0 here. That would happen here. So what are we saying here? We're saying that x sub 1 plus x sub 2 plus x sub 4 equals 0. In the second row, we have the fact that x sub 3 plus x sub 4 equals 0. And then last row, we just have zeros. We just have all zeros. So that doesn't help us at all. So what do we want to do from here? Now, in these circumstances, let's just look at that first one. And there are 4 unknowns. And I have 3 in that first one, so it's very easy for me to alternatively make this a 0 and this a 1, and then make this a 1 and this a 0, and see what happens. So if I make 2 a 1 and this a 0, that means x is minus 1, x sub 1 is minus 1. I made this a 1. Now what happens to 3? Well, if I made this a 0, this means x3 must also be 0, and I made x4 a 0. So all I'm doing here, I just solved this first equation for x sub 1. So that's minus x sub 2 minus x sub 4. And this second one we can also make, that is minus x sub 4. So in the first instance, I made this a 0 and this a 1. That made x sub 1 negative 1. I made this a 1, so it is there. If I made x sub 4 a 0, x sub 3 is a 0. Now I'm just going to swivel that around. I'm going to make x sub 4 1 this time. So I'm going to make, so this was in essence making x sub 2 into 1. But there's linear combinations of that. If I could have made it a 2 or a 3, doesn't matter. This would be sort of the simplest form I can get to. And if I make x sub 4 a 1 in this instance, and that means x sub 3 is going to be a negative 1. And if I made this a 1, where are we? If I made this a 1 and this is 0, x sub 1 is still minus 1. And I made this one a 0. And this was x sub 4, remember, that I did. I made x sub 4 a 1. And what we are saying here is, now this is going to be different because there's not a 0 there. There's a 0 and there's not a 0. There's a 0 and there's a 0. But there are not 2 zeros there. So I can't just say any linear combination of this. It's got to go to our special. It worked out for us, especially in our previous examples, that there was a 0 there, for instance, and I could do linear combinations. But what we are saying here is linear combinations of these two. And in our instance here, making x2 1. And there we made x4 1 and x2 0. There x2 was 1, there x4 was 1, x4 was 0, and x4 was 1 and x2 was 0. So let's do linear combinations of those. So that is going to be minus x2 minus x4. There's going to be an x2 there. I'm just adding them up. And there's going to be a minus x4. And there's going to be an x4. And there, that is linear combination of these two. What we are saying is that these two special cases, that special case and that special case, that is our null space. Those are special cases in our null space, at least special cases. Special cases. So I can plug this one in there. This one, I can plug this one in there. But if I want to look at the whole null space, it is linear combinations of these together with this, So in that instance, so now if I set, let's do something very wild. I'm going to set x, let's make x2 equal to, let's make that negative 3, and I'm going to make x 4 into 6. That means a linear combination of this is going to be minus 3, that's 3, minus 6, and x2 is minus 3, and x4 is 6, so that's minus 6, and x4 is 6. So I'm left with this, I'm left with minus 3, minus 6, 6. That would also be in my solution space, so that makes up this whole null space. So be very careful when you look at these. And sometimes this feels very tricky, you know, what do I do? Solve each of these lines for our pivot here, which is x1, that one's x3. And then this first one is very nice because I can just play around with these two, which means it gives me a solution to this. So alternatively make this 1 and 0, and make this 1 and that one 0, which gives you, if you make x1, x2, if you make that equal to 1, this is your special case. If you make this one 1 and x2 0, this will be your special case. But the linear combinations of these are the linear combination of this, which is that. So I can plug in values for, this is my x sub 1, this is my x sub 2, this is my x sub 3, this is my x sub 4, so that I end up with this. If I make x sub 1 this, and x sub 2 this, and x sub 3 this, and x sub 4 this, I have a solution to my, that will be a solution. Linear combinations of these will give me a solution to this problem that I have here. So very, very important for you to realize how to construct these two. And it is linear combinations of these two special cases in this form, which will give me possible solutions. And that null space, that is a special, that is a subspace. This null space is a subspace in R4 if we took that, all these coefficients here and all the solutions here must be real numbers. This will be a subspace of R4 called the null space of our initial problem. So I hope you see that distinction from what we had yesterday. So here we are in Mathematica, and let's have a look at this example that we just had on the board. I've created the augmented matrix here. I've called it uppercase A, lowercase a, could have called it anything. And let's just hold down Shift and Enter. It is there. Let's just look at it in matrix form. And you can see other, different from what I had done on the board, this is the augmented matrix. And let's get that in row reduced form. So row reduced A, and I want to see that in matrix form as well. And you see all these zeros on the right hand side, it's going to work out like that. This is all the right hand sides are equal to 0. So in effect, if I were to read this off, it says 1 times x sub 1 plus 1 times x sub 2. There's no x sub 3s there, so x plus x sub 4, that's 0. And there I have an x sub 3 and x sub 4 is 0. And I solve here, x sub 1 is then minus x sub 2 minus x sub 4, and x sub 3 is minus x sub 4. And I'm going to just look at that first one, because you can see x sub 4 is in the second one. So alternatively, I'm going to make x sub 2 1 and x sub 4 0 to solve for x sub 1. And because I made x sub 4 0, I also have a solution for x sub 3. And then I'm going to swap it around. I'm going to make x sub 2 a 0 and x sub 4 a 1, which also gives me a solution for x sub 3, whilst giving me a solution to x sub 1. Okay, so let's carry on. I've just now made the matrix of coefficients. I've left out the 0, 0, 0. I want to do that because there is a null space function inside of Mathematica, but you can only enter the matrix. Remember, we are writing AX equals B. We are really interested in that matrix of coefficients, not really the augmented matrix. I just did the augmented matrix here just to show you how we get, just an easy way to see how we get then from here to these equations that we have here. So let's just have A, and now I can call null space of A. It's going to give me 2 rows, but I actually want the column view, so I'm just going to transpose it. Remember to always transpose it when you print it out to the screen with a null space, and I want it in matrix form. And there we go. I should say the null space of A. And there we go. And we see what we had on the board, the -1, 0, negative 1, 1. It's just in the different order than we had. Here we can see x2 is 0, and in this one we see x4 is 0, and here in the first one x1 is x4, x sub 4 is 1, and here x sub 2 is 1. So it's just in the reverse order, but it gives me that exact null space. So just as we did on the board, the Mathematica is going to give you this exact same solution. Now let me show you how we can just test what we did on the board. So I'm going to show you how to construct a function in Mathematica. I'm going to call my function f1, and I'm going to, inside of square brackets, give it all the variables that we are dealing with. Just as you would have done in algebra or in calculus, you say the f of x, or in multivariable calculus, you would say the f of x comma y. So let's put in x1, but to tell Mathematica that this is a placeholder variable, I'm going to put an underscore after that one, comma. There's an x2. I'm not going to do the subscript notation. I'll just keep it easy like this. Underscore. I have x3 underscore, and I have x4 underscore, and I underscore. There we go. And I close my square brackets. Now, I don't want any immediate execution here or any immediate equation of the right-hand side to the left-hand side. So I'm going to use this notation, colon /. And look what happened. These turned like a greenish color, and the colon means don't execute now. This is just a placeholder function that I'm creating. So just as NullSpace row reduce was a function, I am creating my own function. And one of the functions I can create is just normal mathematical functions. And remember our initial thing we had here, it was a system of linear equations. So that said it was x sub 1 plus x sub 2 plus 2 times x sub 3, and instead of times I'm leaving a space between the 2 and x sub 3, plus 2 times plus, what did we have, 3 times is a space, x sub 4, and I'm going to put a semicolon because I don't want that expressed to the screen. So let's press enter, and I'm just going to copy and paste here from my second screen the other two. So all I'm doing here basically is recreating my linear system that I had initially, and they all equal to 0. And you know, the trivial solution is, let me show you that. Let's hold shift and enter. Let's do the trivial solution. I'm going to say f1, and the placeholder, see that it's just like a Mathematica function now. I have all these arguments that I have to pass to my function. It's just so happens to be this time around a mathematical function. So 0, 0, 0, 0. If I were to do that, I get the solution 0. That 0 vector is a solution. But let's do something special here. Let me say a new style, and I'm going to choose, I'll bring it in for you, I'm going to choose display formula numbered. Let's do that. And remember, this first one was x sub 4, and the second one was x sub 2. So let's make x sub 4. Let's redo that. Let's make x sub 4. Let's make that equal to, let's say, 6. And we're going to make x sub 3. X sub 3, we're going to that equal, say, negative 3. And remember, this was in reversed order, so this first one was x4, and this one, that should be x sub 2. The second one was x sub 2. So let's just do that and see where we get to. So I'm going to say minus, this minus negative 3, times this minus 1, that's 3, minus 6. So I'm going to end up with, I'm just going to do some placeholder text here. So that first one is going to be a negative 3. And if I do minus 6 times 0 is 0, and a minus 3, so that's also going to be a minus 3. And if I do 6 times minus 1, that's minus 6, so this is going to be a negative 6. And if I do 6 times 1 is 6, and the negative 3 times 0 is 0, so there I'm going to end up with a positive 6. I'm just doing a little placeholder work for myself there. And let's see what happens if I take f1 and I pass this now. It's negative 3, negative 3, negative 6, 6. And if I pass that, it is 0. That is a solution. So remember that you have to multiply this first null space here, that's x4 times this plus x2 times this second one, and that's going to give you a new solution in the subspace, and you can check any one of these. Let's just make sure. Let's just do f2 there. f2 was, let's do a -3, comma, a -3, comma, a -6, comma, 6. If I were to do that, also 0. So that is a legitimate solution. Let's just check f3 as well. And it's -3, comma, -3, comma, -6, -6, and a 6. Close there. It's a solution. That linear combination of x4 times this first one and x2 times the second one gives me a new vector. And I've just wrote it here just for convenience sake because I didn't want to remember -3, -3, -6, -6. But I've created this function called f1, f2, f3 to represent my system of linear equations. I pop in this new solution there, I pop in these new there, and I do get zeros. So I know that this is a solution. It is in this null space, which is a subspace of R4. It's R4 because we're dealing with 4 dimensions here, 4 unknowns. And you see how beautifully this works out. And you can also see my two special solutions here. And linear combinations of those, remember with the x sub 4 and the x sub 2 there, those linear combinations make up the full null space.